Okay, this is an example from your module test that I wanted to do with you guys. So this is for your series resistive reactive circuits. So a series circuit that contains a resistive load, so an in-phase load and an inductor with resistance, or an in-phase resistor and a capacitor. So not a full RLC, but a series resistive reactive. So in this particular circuit, I have an in-phase resistor, could be a heater or a lamp, in series with a coil, and the coil has resistance in it. So I am given the volt drops that are across both loads. I am given the voltage of the circuit, so my E total. I'm given the current that's flowing through the circuit. So it says solve apparent power for the coil. So I am going to use the triangle method to solve for that unknown variable. So the first thing that I'm going to do is I'm going to draw my triangle sets for this particular circuit, all right? So I'm dealing with a series circuit, so that contains an impedance triangle, a voltage triangle, and a power triangle. I draw all triangles regardless if I populate them or not. It's important to have them there to visualize their placement and to keep you organized with your next step. So an impedance triangle, I'm going to draw the triangle below the load the load that they belong to. Okay, so impedance triangle for a resistive load, for example, a lamp. An impedance triangle for that lamp is just a straight line. Okay, an in-phase load, meaning that current and voltage are rising and falling at the same rate. So whatever value of impedance, it would be found at 0 degrees. Okay, and then I'm going to add that to a coil. So the coil has a variable of in-phase resistance in it. It is a component that is constructed of copper, many turns of copper wire. Therefore, it is going to have a variable of resistance in it. Okay, so this would be, so first of all, that would be my R of the resistor. Okay, so then the coil has a resistive component. I'm going to label that RC, so the resistance of the coil, as well as it's going to have an XL component because it's an inductor. And then the vectorial sum of those two sides would give me the impedance for the coil. Okay, and then this over here on the right hand side would be my circuit totals. All right, so the resistive portion of my lamp is in phase with the resistive portion of my coil at 0 degrees. So these two values are additive. So that would give me an in-phase component of a resistance total because they're in phase with each other. And then, sorry to go so far there, my vectorial or my vertical would be my XL. So whatever value of XL is here would be brought over to my circuit total because there is no component of inductive reactance or capacitive reactance found in the circuit. Okay, and so then the voltage triangles for this circuit would look like this. So the volt drop across the resistor would be an in-phase volt drop, so VR, plus the volt drop across the resistive portion would be my VR coil, in-phase volt drop, that's vectorially added to the volt drop across the VXL, okay? And then I would add them together vectorially, meaning using Pythagorean, and that would give me my volt drop across the coil. Okay, so then I can take the volt drop across the resistive component in phase with the volt drop across the resistive component of the coil to give me a VR total. And then whatever the volt drop is across the XL component would then be brought forward over to your circuit totals, being that there is only one variable of inductance and there is no capacitance in the circuit. And then the sum of these two sides vectorially added using Pythagorean would give me my E total. Okay, and then my power triangles are drawn the same way. So the power that's dissipated from the in-phase resistor or lamp would be PR at 0 degrees. Being added to my coil, the coil has an in-phase resistance, therefore it's going to dissipate true power, so PR coil. And then my power that's being dissipated from the inductive reactance portion is my QXL, and then the vectorial sum of those two sides would be known as apparent power for the coil, and ultimately that is what we are looking to solve in this particular question here. Okay, and then the triangle total, so the power that's dissipated in the resistor is in phase with the power that's dissipating for the in-phase component of the coil. So that would result in PR total. And then whatever reactive power is being produced from my inductor would then just carry forward over to my circuit total. And then the vectorial sum of those two sides would be my S total, apparent power of the circuit. So yeah, I'm not going to fill in every value for every triangle component because I don't have to, but it allows me to see the connection between all of the variables. Okay, so the link in a series circuit is your current, which was given to us. So they told me that my current is 1.376 amps. Okay, so that is the link. I'm going to take the volt drops that were given, and I'm also going to put them in the proper placement for this circuit. So they said if you were to put your voltmeter across this lamp or resistive load, that would give you 30.267 volts. So that would be VR. That would be the volt drop across the resistor. Okay, so that's 30.267 volts at 0 degrees in phase load. Then the volt drop across the coil. So I want you to be mindful that a coil incorporates an in-phase volt drop as well as an inductive reactive volt drop, and those are 90 degrees out of phase with each other. But to actually physically put your multimeter in there and get a volt drop across the coil as opposed to a volt drop across the resistor, you would have to be inside of the housing of a motor per se. So a motor is a good example of an inductor. When you are doing a volt drop across a motor, typically you do not have access inside of the housing. You're metering your volt drop across the two leads of the motor, which would give you the volt drop across the entire portion of the inductor, right? So when they say the volt drop across the coil is 114.313, you need to recognize that volt drop represents the hypotenuse of your voltage triangle for that coil. And that is a very common mistake made by many apprentices. They will take that volt drop and either put it in the resistive portion or in the inductive reactive portion, and that just throws off everything. Okay, so right now I took the volt drop of the resistor and I populated it in the volt drop for the triangle. For the resistor. The volt drop for the coil is the hypotenuse of that triangle. They also did give me the voltage for the entire circuit, right? So that is always the hypotenuse of your circuit total. And that might be useful in us trying to find the apparent power of the coil. That's what we're looking for. So now I've taken all the information that was given to us in the circuit. I've populated it in the correct placement for the triangles. I have the current that's flowing through the circuit. Therefore, I have the link between the triangles. So I want to find the apparent power that's being produced by the coils solely. So I want everyone to recognize, because I have the volt drop that's across the coil, using my current, so times current, I am taking voltage times it by current to give me apparent power. Okay, so that is the link. So for me to find my SC, I'm going V coil times current. Current is constant, okay? So V coil is 114.313 volts times the current, which is given to me, 1.376 amps, and that gives me the apparent power of the coil, okay? So 114.313 times 1.376 equals 157.29, and the unit of measurement for apparent power is VA. Okay, so that is your answer, 157.29 VA.